Hello, colleagues, and I'm so sorry, I cannot be, on site after Corona. Somehow, my September became, quite chaotic, and I couldn't, make it, unfortunately. So, but taking this opportunity, let me speak about our thermal transport study on Kitaev candidate magnet, and this particular work was done in collaboration with those people listed here, and in particular Jan Bruin, Ralph Krauss, Yosuke Matsumoto. Those three are kind of key player of this particular project. So I'm sorry to start with this stupid view graph for this audience, but anyway, so quantum spin liquid is kind of exotic state of matter, highly entangled object, and resonance valence bond state in a triangular based magnet has been kind of a only playground for this subfield for long, but recently Kitaev brought a new generation of quantum spin liquid, and that's how story began. And Kitaev proposed simple but quite elegant model on the honeycomb lattice, and he placed the spin 1/2 moment on top of a honeycomb lattice, connected by 3 Ising bond with easy axis X and Y and Z, and the conflict of those 3 Ising bond give us frustration in spin degree of freedom, and this give rise to quantum spin liquid. And as of course better than me, this is exactly kind of a solvable, unlike will be. Okay, and as a result, spin 1/2 fractional into Majorana fermions, which give rise to iterant Dirac coming from this C Majorana, and the G2 flux coming from the bond Majorana B. And this Dirac-like part under magnetic field, Kitaev already in his seminal paper mentioned it can be gapped, and because of the gap topologically protected, and this gives rise to Majorana edge state, and of course Majorana kind of neutral particle. This edge state cannot be probed electronically, but can be probed thermally. And in fact, Kitaev showed this Majorana edge state can be probed by quantized thermal Hall effect, quantized like this way. And this 1/2 come from only one of the 2 Majoranas, iterant and flux localized. Only one iterant Dirac contribute to this business. And having this many people, many experimentalists try to get into this field, particularly it was triggered by theory of my Stuttgart colleague George Jacqueline and the Guignard Caroline, and they showed using J1/2 moment instead of spin 1/2 moment, coming from elements such as iridium 4+ or ruthenium 3+, we can materialize the Kitaev model. And that kind of motivated us. So they proposed, if D5 iridium 4+ or ruthenium 3+ are placed in anion octahedral, cage. Okay, so you have, one hole in T2G orbital, and this, give rise to, orbital moment of 1 and spin 1/2. And the ground state, you have, J1/2 state, L minus S. Okay, and this state, look like, S equal 1/2, but because, this is, spin orbit, complex, story kind of different. In particular, if you connect, two octahedron by edge, okay, so the interaction between two neighboring J1/2 is, quite, aging like, fellow. So the reason is, because, in a edge, shared, coupling, you have two exchange paths, because of two options, here, and that, profit the direct, hopping of a J1 moment, from, one side to next side. So the only way is, hop to, upper J3/2, state, and this, front coupling of, excited state and the ground, state, give rise to, fellow, coupling. And also the presence of L equal 1, give rise to, quite, Ising like, coupling. And by having, Ising, coupling of J1/2, spins with, edge shared spin. Okay, so this is the essential ingredient of a Kitaev model. Now, we can play with some kind of Kitaev, Lego, right? So as I said, those, edge, shared, coupling give rise to, Ising, like, coupling with, easy axis, perpendicular to bond, plane. And as you notice, those, octahedron has, 3 orthogonal edge, okay? And using those, 3 orthogonal edge, you can make a 120-degree bond. And, each bond, give rise to, ferromagnetic aging coupling, but easy axis is, orthogonal to each other, X and Y and Z. This is, nothing but, what, Kitaev model tells us. And once, having this, 120-degree bond, okay, so you can form a Honeycomb RuCl3, like this, using, edge sharing, octahedron. And fortunately, we are kind of material physicists, and we knew, many compound has, honeycomb, structure made of edge, shared, octahedron like this, with, D5 iridium 4+ or ruthenium 3+ moment. And everybody rushed into this business and tried to, discover, quantum spin liquid. But unfortunately, most of, those, compound showed, anti-ferromagnetic ordering, not, spin liquid, likely due to additional interaction. And this, view graph showed, how hard, experimentalists, worked on this, business. Here is a list of, compound having, honeycomb, rallies and, pewter zip, Kitaev, quantum spin liquid. And yeah, you see kind of many compound. But among them, okay, so most of them, shows, magnetic, ordering. Among them, so far, only 2 showed, quantum spin liquid-like behavior. One is, hydrogen lithium iridate, okay, and the other is, ruthenium chloride, under magnetic field. The rest, you see magnetic, ordering. But maybe, compound with green, you may see some, interesting character. For example, ruthenium, iodide, this is kind of a sister compound to ruthenium chloride. This compound known to be a metallic. So this is a metallic analog of Kitaev candidate. And recently, cobalt compound, okay, 3D7 attracts, some interest as, Kitaev, candidate. And in particular, this, barium cobalt, compound, we have, zigzag, magnetic ordering, like ruthenium, chloride. But under minutes of magnetic field, this ordered state collapse like ruthenium chloride. So just pay attention to those compounds. Okay. But anyway, so today let me speak about those two compounds. Okay, discovered to host quantum spin liquid. And the hydrogen lithium iridate. Okay, we discovered 4 years ago, and lithium iridate, okay, is kind of first honeycomb compound. People discussed that possible Kitaev quantum spin liquid state, but unfortunately they do show long range magnetic ordering. And what we did was use soft chemistry. And replaced lithium in between honeycomb layer with proton. Actually, this compound was previously studied as pH sensor material by chemists. But somehow replacement of lithium with hydrogen proton gave us something magical. Okay, so this is NMR data for lithium 7 at the center of honeycomb and hydrogen. And if you have any kind of magnetic ordering, you would expect broadening or split of those peaks. Okay, due to inhomogeneous distribution of magnetic field. But as you see, with lowering temperature, those peaks get narrower. You don't see any broadening of peaks. Okay, so that indicates absence of magnetic ordering. And then we confirmed absence of magnetic ordering down to 50 milli-K. And magnetic coupling is of the order of 100 K. So this is practically kind of low temperature limit. And from the absence of magnetic ordering, we concluded quantum spin liquid ground state is realized in this compound. And of course, immediately we started hunting signature of Majorana in this compound. But at this stage, our understanding is this compound is extremely interesting quantum spin liquid, but not ideal playground to hunt the Kitaev physics. And this is kind of the one of the reason why we believe some other ingredient plays quite important role. So what we did was we did so-called isotope experiment. Like superconductor. So we replaced hydrogen with deuteron. Okay, so mass is kind of doubled. And you don't expect any isotope effect for magnet, okay, unlike superconductor. But in reality, we had a huge isotope effect on magnetic coupling. Okay. So like if you take a look at the Curie-wise increase, okay, at high temperature, we found the Curie-wise temperature is doubled from 100 K for hydrogen to almost 180 K. Okay, and we believe this is kind of a modulation of exchange coupling. Through coupling of hydrogen deuteron. Okay, so we kind of established a giant isotope effect on magnetic interaction. But as you see from this figure, at low temperature you don't see any signature of magnetic ordering. Somehow, despite, big change in magnetic interaction, quantum spin liquid is quite, robust against, isotope exchange. And of course, Kitaev, quantum spin liquid, state is known to be quite, sensitive to the change of exchange, parameter. So such, robustness, cannot be expected for pure Kitaev. So that's, why we believe some, ingredient, other than, pure Kitaev, possibly, disorder, must be involved. Okay. And in parallel with, those, discoveries, other, Kitaev, candidate, compound, come to this business, and that, somehow, as you know, this compound, became, a kind of star compound in the community. So, ruthenium, chloride, chloride is again, 4d5, copy 5, d electron with, J1/2 moment within octahedron. Okay, so they have, the same, honeycomb motif, as, iridate. And then this compound are discovered, already, 8 years, ago, as kind of magnet. Okay. And then they found that, below 7.5 K, this compound showed, some kind of zigzag, magnetic, ordering. Then, people found this, zigzag order is not, quite robust. But if you apply magnetic field parallel to the plane, plane, direction, this, zigzag, ordering, you can see in the susceptibility is suppressed, and eventually goes away, around, 7 Tesla. Okay, so this is a kind of phase, diagram. Okay, and then, this, long range, ordering disappears, around 7 Tesla. And here you see, kind of paramagnetic phase, above the collapse of, zigzag, ordering. And the people, discuss, this, paramagnetic, phase in some kind of quantum spin liquid, state. And in fact, this, field induced, paramagnetic state. People discovered, some, exotic, signature. For example, group of, Stefan Nagler, okay, Oak Ridge, they find, some, continuum, excitation in their neutron, scattering, data. And they suggested that, this is kind of signature of fractionalization of, spin. And perhaps, more kind of closely related to, this talk, half, integer, quantized, thermal Hall effect, as, predicted, by, Kitaev, was, claimed by a group of Yuji Matsuda in Kyoto. And this, discovery or this, observation of, almost, half, quantized, thermal Hall effect, attracted, big, attention to this, compound. And I was a bit, jealous, about that. But then, somehow, hot, debate, comes on their discovery. So, after, original discovery, by, Matsuda, some people, find the difficulty in reproducing, their result. And also some people kind of pointed out that, Matsuda result, needed, to have, some kind of low temperature there. So for example, taking a look at, original, Mazda data, as a function of magnetic field, you seems to have, some, plateau, like, behavior, from say like, 7.5 to 8.5. Okay, so look like, quite, plateau. But as a function of temperature, okay, so they measure only down to 3.5. And so this, figure is kind of expansion of this part, kind of rapid decrease of, thermal Hall effect. But since, they lie down to 3.5, so, it is not, clear whether thermal Hall effect just, cross, half, quantized, value, or it shows, some kind of, temperature plateau. And this kind of brought, some kind of a debate, whether there is, any clear-cut, temperature plateau or not. The group of, Fan Ong, from, Princeton, they, published their kind of thermal Hall effect data, last year. And they said, this, thermal Hall effect is, roughly 1/2 to 1/3 of expected, quantized, value. And also, they see, they observe just, kind of broad peak, not, plateau state. And so therefore, they said, they didn't reproduce, Matsuda data. But nevertheless, Ong group, kind of reported something interesting, happening here, okay, in ruthenium, chloride. So here is, temperature dependence of kappa XX, non-regional, not, thermal Hall effect. This is just, thermal conductivity. Okay, and the group of, Fan Ong, discovered, quite oscillative, or oscillatory behavior of, thermal, conductivity, like this. And they, plotted those, peak and the deep, position as a function of 1/h. And from that, they kind of claimed, it is, some kind of quantum oscillation from neutral quasi particle. Okay, so somehow something, exotic, must be happening, there, but some, confusion there. Okay, and since, I wanted to work on my own, compound, I had been staying away from ruthenium trichloride, but somehow my young, colleagues were interested in this, chaotic situation, and I wanted to, work on ruthenium trichloride to examine, quantization of thermal Hall effect and the oscillatory structure kappa XX. And simply, I couldn't, stop, my young colleague to work on ruthenium trichloride. So in that sense, all credit on my young, colleagues. Okay, so since, group of Matsuda and group of, Fan Ong, they used, quite, different, category of, crystal. So Kyoto group, Matsuda group used, so-called Bridgman crystal from, TIT. And the Princeton group and, most of others, used, so-called CVT, chemical vapor transport, crystal. Okay. And somehow, we thought, those, differences in sample, might be origin of, kind of confusion. So therefore, we used, both, kind of Bridgman grown crystal and the CVT grown crystal. And the Bridgman crystal, we obtained the same, batch of single crystal as, Matsuda group, used. So I have to thank, Matsuda-san, allowing, to use, same source of crystal. And the CVT, we used, CVT crystal, grown by the group of Bettina Roch in kind of Stuttgart. And we checked X-ray. And even at room temperature, we find, somehow, big difference between two crystals. Okay, so Bridgman, crystal, is kind of monoclinic, and honeycomb RuCl3, stacks, okay, along a direction like this. So you have well-defined, kind of twofold, symmetry along, a-axis. But this CVT crystal has hexagonal in itself, and stacks like alpha, beta, gamma. Okay, so they have kind of a trigonal symmetry. Okay, and the three axes are kind of equivalent. Okay, so in terms of stacking, those two are quite different. Okay, but nevertheless, okay, as I showed in the kind of following view graphs, as a first approximation, they are kind of thermal transport properties are similar to each other. Okay, first we checked kappa XX as a function of temperature, and you see quite well-defined magnetic ordering at zero field. And below, magnetic ordering, you see kind of enhancement thermal conductivity, likely due to, enhancement of phonon thermal conductivity due to the reduction of magnetic, scattering. And with, kind of increasing magnetic field, you can see, this, magnetic ordering temperature is kind of suppressed, suppressed. And around the 7 Tesla, it's kind of disappeared, completely. And after magnetic phase transition goes away, you start seeing enhancement of magnitude of thermal conductivity, which is likely due to again increase of thermal conductivity due to the presence of excitation gap in magnetic excitation channel. Okay, and this kind of will reproduce, previous, result, published, so far. Okay, then, first, we checked, kappa XX, thermal conductivity, oscillatory structure. Okay. So first, we did magnetic field scan at 2K. Okay, and here is our data for Bridgman crystal, the same as Kyoto, and the CVT crystal, the same as kind of Princeton. And green is data from the paper by Professor Ong's group. Okay, we just reproduced it from their paper. And somehow you immediately notice, this, oscillatory structure will reproduced. And we see, kind of deepened peaks, okay, around the same, magnetic field, okay. So we can identify kind of a dips at H1, H2, H3, okay, and H1, H2, H4, 5, 6. And comparing, those, three samples, we notice, Bridgman sample shows, higher thermal conductivity than CVT crystals in general. And higher thermal conductivity means, better crystallinity. But, taking a look at the magnitude of oscillation, Okay, so you see, Bridgman sample shows, kind of a smaller oscillation, magnitude. Though, in general, crystallinity appear to be, kind of better for Bridgman, crystal. And of course, generally, quantum oscillation, higher conductivity sample shows, bigger oscillation, or better sample shows, bigger oscillation. So it is, already kind of against, canonical behavior of, quantum, oscillation. And in fact, if you do see, this, figure, okay, there is, the largest, structure at, H, C1 and HC2, something like 6 Tesla and 7.5 Tesla. And this, deep, field actually coincides with, the collapse of, zigzag, two collapse of, zigzag, ordering at, 6 Tesla and 7.5 Tesla. Okay. And in that sense, we believe, it is natural to understand that those, two deep, structure at, HC1 and HC2 due to, suppression of, phonon thermal conductivity. Okay. So in this, temporal region, thermal conductivity is still dominated by phonons. And scattering of soft magnetic excitations at at the collapse of magnetic ordering give rise to kind of suppression of phonon thermal conductivity. We believe that's kind of more kind of reasonable understanding of at least those two deep structure at HC1 and HC2. And in fact, we believe those oscillatory structure comes not from quantum oscillation, but something else. We have a few firm experimental evidences. First of all, if you take a look at temperature dependence of those oscillatory structure, okay, ongoing from 2.5 K, you see first oscillatory structure gets kind of bigger and bigger, but below 1 K, somehow those oscillatory structure decreases and eventually almost phase out. Okay, and this is kind of look like associated with suppression of phonon contribution at low temperature. Okay, so this is kind of a temperature dependence of the magnitude of kind of oscillation, and both CVT crystal and the Bridgman crystal, you first see increase of structure, but below 1 K, both shows kind of decrease of kind of oscillation. And of course, this decrease of oscillation amplitude is unlike quantum oscillation. To be more precise, Lifshitz-Koszewicz behavior.
We are slightly running out of time, so I was maybe in a couple of minutes, and then we could take some questions. Would that be okay?
Oh, okay. So I'm sorry.
No worries. Okay. You can take it. Just
okay. But anyway, so and somehow we believe this is this is not kind of a quantum oscillation, but something else, and we believe this come from kind of a collapse of minor 10K, 30K, 13K transition. As you see, we have 7.5K magnetic phase transition. On top of that, all sample, okay, even good sample contains some signature of 10K, 30K kind of transition, which is enhanced by doing a kind of mechanical kind of bending experiment. Okay. And we kind of, traced, how, 13K, 10K, transition, in addition to 7K transition is suppressed, by applying magnetic field, by tracing magnetic susceptibility. And we see kind of all those, deep structure is kind of smoothly, connected to 13K, 10K, and the 7K transition. That's why we do believe that, those, high field, anomalies are kind of connected to magnetic phase transition rather than quantum oscillation. Okay, maybe I can skip. And as a kind of a final kind of confirmation, we did kind of a mechanical bending experiment, and somehow after mechanical bending, this deep structure at HC1 and HC2 is kind of enhanced. Okay. So this is kind of separation of so-called main 7K phase. But other features like H3, H4, H5, H6, all kind of enhanced. And this is kind of consistent with increase of minor, 10K, 13K, phases. Okay, and from this, we kind of firmly conclude all those, structure come from, magnetic phase, transition. And maybe, using the last, 1 or 2 minutes, let me discuss thermal Hall effect. And so here is, thermal Hall effect of the same, exactly the same, sample. And as you see, above, 7 Tesla, you see a large, thermal Hall kind of a signal. And okay, and below 10 Tesla, okay, so we have, value close to, half quantized, value, around the 8, 12 Tesla. But, within a degree temperature, it is kind of suppressed. But above, 11 Tesla, somehow, we see kind of a large, residual thermal Hall effect, down to kind of a low temperature. And it is kind of clearer, by doing a temperature scan instead of a magnetic field scan. So this is temperature dependence of a thermal Hall effect. Okay, above magnetic critical field, and below 10 Tesla, you see kind of a monotonic decrease of thermal Hall effect, crossing quantized value. So no plateau state. But somehow above 10 Tesla, you start seeing something like kink. Okay, around the quantized value, and also low temperature part, thermal Hall effect is kind of enhanced, and eventually around 13 Tesla, you see something like temperature independent plateau. Okay, and here is kind of summary of the result, and the white region. It indicates quantized value plus minus 15% okay, and as you see it is something like line, but above kind of 11 Tesla you see extended region of thermal Hall effect close to quantized value. Okay, over wide field temperature region, and the presence of this region is not inconsistent with quantization, and hence Majorana edge state. But of course, this is not inconsistent with Majorana edge state. But at this stage, I have to say it doesn't exclude other scenarios, like magnons and phonons. Okay, so first of all, our resolution is not good enough to verify precise quantization, like electric quantum Hall effect. We have big error bar, and since it like sigma xy, kappa xy is thermal Hall resistance divided by scale of thermal resistivity. And since, this, thermal Hall resistance, decreases kind of rapidly, which is kind of compensated by, decrease of thermal Hall kind of resistance. So, this dissolution at high field is kind of very much kind of limited, and that give us some limitation. And besides, comparing, data with Matsuda group, we notice the field region where we observe, quantization depends, very much on measurement sample. And as I mentioned, the first, data by, Matsuda, they observed, plateau state, from 7.7 to 8.7. But they are kind of recent, data, okay, by kind of Suetsu group, they observed quantization from 10 to 11.5, up to, this, so-called, deep field H6. And then we observe, the value close to quantization, at least up to 13 Tesla. So it kind of depends, very much, on the kind of a measurement. Okay. And then besides, this is kind of a final slide. Yeah, phonon could contribute to, kappa XY. So naively, you might, say, kappa XY should be dominated, only by non-phonon, contribution. But in reality, phonon could, contribute. For example, Ahim Ross, discussed, phonon edge mode, coupling quite important, and kappa XY could be only approximately quantized, when phonon mean pass, doesn't reach, ballistic limit. And in fact, by measuring kind of a system of, almost, quantized, electric, quantum Hall system, we do see kind of, deviation from, Wiedemann Franz behavior, and which we believe, some kind of phonon drag effect, right? So this is kind of firm evidence that, even quantized Hall effect, phonon could, enhance thermal Hall effect, through kind of a phonon drag. And with, that kind of, phonon, contribution, we have, kind of big, ambiguity. So we need more kind of sophisticated experiment. That's kind of our conclusion. So this is kind of my conclusion slide. And thank you very much for your attention.
We have time for one or two quick questions. Yeah, Professor Bhaskar. Yeah.
Hide, wonderful talk.
Yes.
Virtual welcome to Bangalore.
Yes, I'm sorry, actually, yeah.
This is Bhaskaran. So thanks for a wonderful talk.
Hi, hello.
So I'm very happy theory is safe with respect to half quantization.
Yes.
Because I'm very happy to see all the complications are related to materials and the coupling to phonons.
Yeah.
So the spin liquid theory seems to be safe.
Yeah.
So I just wanted to ask a question about your hydrogenated iridium system.
Yes.
Is there any signal of dielectric anomaly related to some cooperative proton ordering or disordering in your earlier system?
Okay.
Because it looks like a hydrogen bonded ferroelectric.
Yeah. Okay, yeah. I didn't mention that, but yes. Yeah. That's a very good question. And okay. So okay, this figure, we wrote, proton is located, exactly, halfway between the upper layer and the bottom layer. But in reality, the hydrogen is, forming, some sort of covalent bond with, oxygen above and below. And some people suspect that, there are kind of two, hydrogen, position Okay, and you might have some sort of a quantum tunneling between the two sides, and our Augsburg colleague did some spectroscopy, far infrared spectroscopy, and they claim some kind of anomaly at low temperature, which they ascribe it to quantum tunneling of kind of proton.
So dielectric.
So in that sense, yeah, that could be kind of related to kind of formation of this quantum spin liquid state.
Thank you.
Okay, so I think in the interest of time, I think we can wind up. So let's thank Takagi again for a very nice talk.
Yeah.
And,